Hello again. I'm very happy to see you. In this video, we will recap the story first, stories of hombre A, B, and C. Hombre is a Spanish word that means a man. And then we would continue that story into the bigger challenges they face now and how they tackle them. And importantly, we would also go into the historical process that led to these thoughts, because even though the hombre A and B are fictional, we are talking about the same universe that they live in. We live in the same universe. So in the end, I will talk about the history of physics that and astronomy that led to this next step in realization about what is the universe that we inhabit in. And I would also show you a simulation on stellarium. Very nice. Okay, to recap quickly, there was an hombre A who was born in a room with a ball and a ruler and a clock. He let the ball go, the ball remained there. He pushed the ball around, it jumped around, and then he came up with a coordinate system for the ball, x and y. And then he came up with the laws of physics, the laws of reflection, how hard do I hit, how fast the ball moves, and so on and so on. And one day he discovers that there was another room next to his room, exactly the same, with another person, hombre B as we call him, who has also been doing the same things as hombre A, and who thinks that his is the original room and hombre A's is the other room. And hombre A thinks that hombre B's room is the other room. And now once they do the experiments, they realize it's exactly the same. The only difference is that for hombre A, the balls is just a distance d shifted away, and then it's doing the exact same thing. So all he has to do, hombre A, when he measures the distance to hombre B's ball, which is xa, which is a bigger distance, all he has to do is just subtract the difference between their origins, and then he gets the distances as measured by hombre B. So why remains the same? Because the room is only moved in the x direction, and the moment hombre A also takes the positions with respect to time for the ball, and then he just has to subtract the d, a constant number, from his x values, and then he gets the same values that hombre B is measuring. So they conclude that apart from this shift, the rooms are identical. All the laws of physics are the same. So this is the first, like the very basic relativity, that no matter where you are in the universe, the laws of physics are the same. So the space that we inhabit is homogeneous. And also, no matter where you throw the ball, it goes in the same direction given you pushed it the same. So the unit is also isotropic. Don't worry about the word isotropic. It just means that all the directions are the same. There's no, preferred direction. And then one day, problem comes when hombre A and hombre B see hombre C, a third room, who has also been doing exactly the same thing, blah blah blah, and now they're concerned about whether he leaves the ball there, would it remain at the same distances that hombre A and hombre B measure, or would it remain at the same distance as hombre C measures? And it turns out that it remains at the same distances as hombre C measures. So hombre C's room just translates forward, and the ball remains at the same distance from hombre C, but the distances from hombre A and B have changed, and it's a continuously changing distance for hombre A and B. But then hombre C remarks that, wait, I was always here and you guys were who moved to me, I never moved. And now hombre A, B, and C have to come to this realization that not only that the universe, the laws of the physics of the universe are the same no matter where the room is, in what direction it is oriented in, but also if you're moving at a constant speed, it's as if you are not moving at all. So it's also symmetric in that sense, that if you're moving, it's as if you're not moving, given that you're moving with a constant speed. And neither of them can say that their original room, even though it looks like the other room is moving. And that was Galileo's relativity. Now we are going to have uh, a next problem in the lives of hombre A and hombre B and hombre C, but hombre C has now just left and we are with hombre A and B. But let us just recall that when this d, which was the difference between the origins in x coordinate, when this ombre b's room starts moving with a constant speed, then this d is increasing, and to show a number that constantly increases, we can write time. It's a number that constantly increases, and we also saw that if the ball or the ombre c's room, it can move faster or slower, and so you also have this multiplicative factor. If this v is faster than v is bigger, then that means that this room is going away faster. So xa would, so if the ball doesn't move in ombre b's room, so he measures xb as constant, the ball remains in front of his face. But since his room entirely moves ahead, he would ombre a would measure that the distance to the ball is constantly increasing, so he subtracts a constantly increasing number vt from it to get the same distance as ombre b, and then ombre b can do all the same experiments again, even though he's in a moving room. I mean, according to a, because according to ombre b he's not moving and ombre a is falling behind. They all get the same results. You just have to subtract this vt from every x measurement that you make. Okay, now the bigger problem, now let's go to the next problem that they face. Now let us imagine that they're able to drive these rooms somehow at constant speeds. Okay, so this is ombre A and this is ombre B, and now they have clocks. I mean, they always had clocks. And let's say these are stopwatches and they go to maybe 24 hours, they count 1, 2, 3, 4, 24. And then they start the stopwatches at 0, and then ombre B starts moving in this direction, and he moves some distance d. And by the way, from ombre A B's perspective, ombre A moved away from him and he never moved while he was moving at a constant speed. So this is ombre B. Okay, and the ball again. But now a weird thing happens. Ombre B, let us say now he also has a telescope, because why not? He looks at ombre A's watch, and it's in ombre B's watch, it's something like 3 o'clock, but in ombre A's watch, it's 2 o'clock. He thought, what is wrong with ombre A? He's using a broken watch. And but weirdly, in ombre A's frame, it's the opposite. Ombre A thinks it's 3 o'clock and he sees that ombre B's clock is showing 2 o'clock, and he's also annoyed that ombre B's clock is not working. And then they say, just come back. They come back and then they share this problem that your clock was behind, and both of them say the same thing, that your clock was behind. And then they're physicists, so they're curious. How? How is how can we both think that one of the clocks had to be behind? And then they say, okay, let's do this thing. We would drop at 3 p.m. Let's restart our stopwatch, and at 3 p.m. we would just push the ball down like this in our watches, what we can see in the watch that we have, right? So ombre B again moves to the location some distance d away, big D because it's a big distance, and at, well, so this is we have to draw two versions of the clocks. This is ombre A's clock as seen by ombre A, and ombre B's clock as seen by ombre A, and this is ombre A's clock as seen by ombre B, and ombre B's clock as seen by ombre A, because as we saw, they both think, you get the point. And now they both think that they pushed the ball at the same, like at 3. But when ombre A pushes the ball towards the ground, when he looks at ombre B through his telescope, he also has a telescope. He sees that ombre B hasn't dropped the ball. Ombre B is still holding the ball and he's dropping the ball alone, and they decide that we do this together. So what the hell, ombre B, why would you do this to me? And that's the same thing that ombre B is feeling, that why hasn't ombre A dropped the ball? It's 3. But then he looks at his watch through his telescope and he sees that, oh, he thinks it's 2 p.m. So naturally he hasn't dropped the ball because he thinks it's not the time yet. So ombre B patiently watches and it's 3. in, yeah, okay, it's 3. When it turns 3 in Ombre A's watch, Ombre A does drop the ball. So when they meet again, Ombre B comes back and they discuss. They ask each other, why did you not drop the ball on time? But okay, I understand your clock was behind. And then they realize, wait a minute. So both of us dropped the ball at 3 p.m. but and thought the other person had dropped the ball late, or rather an hour later than I dropped. So did we really drop the ball at the same time or not? And this is the question. Who knows? How do we know now if we drop the ball at the same time? Because it did not appear that way. When I dropped the ball, you were still holding the ball. When my ball was here, your ball was trailing behind. So these movements did not look simultaneous together at all. But then what is this deal with this falling behind of thing? So let's do this thing. Let's change this D, go farther away. Now Ombre B goes even farther away, and then Ombre A sees that when it's 3 o'clock in his watch, it's 1 o'clock in Ombre B's watch, and the distance is twice as much. So if Ombre B went 2D distance away, then the time is 2 hours behind. So that means that the distance has something to do with this time thing. Now, as we had seen that for a room that is sitting at a distance D away and Ombre A measures distance A, then you have to subtract that D distance away to get the coordinate measured by Ombre B. But so far we had been saying that the time that they measure is the same, because if they see, like, let us say, some explosion occurring, some supernova explosion, well, there is nothing else in the universe, but bear with me, then they would measure the same time to it, right? But no, not now anymore, because uh, it's clear that when Ombre A writes down 3 o'clock as the explosion of supernova, Ombre B would also be writing 3 o'clock, or who knows what he would be writing. But when Ombre A looks at Ombre B's watch, it's 2 o'clock. But when B comes back, he says that no, I wrote down as 3 o'clock. But Ombre A would think that that explosion occurred at 2 o'clock in Ombre B's time. So now you can't have TA equal to TB if some, like, if this is 2 hour and then like 3 o'clock or 2 o'clock. If this is 3, then it's not, like, when he looks at Ombre B's watch, it's actually behind, so it's not equal. So that means that from Ombre A's perspective, he has to subtract something to get Ombre B's time. So for example, if it's 3 p.m., he has to subtract 1 hour to get 2 p.m. Or rather, if it's 3 hours after they started the stopwatches together, he has to subtract 1 hour to get the time that he sees through his telescope, what Ombre B is experiencing or is thinking that it is. So and we also saw that if you move twice as far, then this number is twice as big, so it's obviously proportional to the distance. Some proportionality constant alpha times distance. Cool. They have sort of figured it out, but then the question again remains that if the star exploded near Ombre B, then he would see it sooner than Ombre A. And now then if he saw it at 3 p.m., now how do they fix this is to, if Ombre A is given the time in Ombre B's clock, then he can figure out the time. Hold on, I need to pause. Where is my... I was confused for a reason. It goes into a little bit more dimension of complexity, so we'll do it a little bit later. My point is that depending on where the star explodes, they would note down different times, but then they can fix that by knowing how much is the distance between their frames, given that the star is also on this line. And otherwise you would have to use Pythagoras, not a big deal. So they can then again find out the time that the other person recorded in their watch. So because they know the relation between their watches, which is fixed. So if Ombre he sees that ombre B has recorded some time in his watch, then he knows what it should be in my watch. Okay. So now, as we talked earlier, ombre B has a question. What if I didn't stay still and I kept going? So my room, why did I erase this? Just to redraw it again. So ombre A's room now, oh sorry, ombre B's room now keeps going. But again, remember that ombre B thinks that he doesn't move and A is going away. What happens then? Because in the case of the previous video, we saw that it was VT, like you have to subtract VT A. So because XA, if the ball doesn't move, then XA is measuring an increasing distance, and he subtracts an increasing number which is VT, and then he gets the constant XB. And in terms of time, we would also replace the time by VTA. Now, okay, so this is basically the new transform that we're talking about. And if you see that if you take TA common here, then it's so that times are not ticking at the same rate. What happens when, see, the time, the stopwatches, they start at the same time, but when this watch starts going away, it starts falling behind, right? So the ticks of this clock are slower than the ticks of this clock. And this is what you see here. So, and this is, I'm not making this up, if something is going away from you, they will appear slower. And this is something that we are going to see in a very short while. Well, shortly. We are going to see it shortly. You can actually see it happening. That if something, if ombre, okay, so again they do the same experiment where they decide to push the ball with the exact same force towards the ground, I mean towards the floor, and when ombre A watches ombre B do it while his room is moving away, he watches it drop slower. Then the question is, did it drop slower? No. You have to, so if you have, position versus time of the ball, so this is, let us say, the y of the ball, which is a function of time, and this is time, then the ball, let us say that it dropped like this in ombre A's room. It dropped like this. I mean, it dropped like this, but then time is on this axis, so it dropped like this, but then we are drawing all the positions of the ball according to time. You know what, how to read graphs. And then this slope, like this tangent of this divided by this, is the speed of the ball, right? Delta y by delta t. But if ombre B's room was moving as the ball dropped, then ombre is going to think that now delta t is bigger, so delta y by delta t dash, y dash also, but it doesn't, is y dash, delta y dash and delta y are the same. Then he would think that since delta t dash is bigger than delta t, then he would think that the ball is dropping slower, which he shouldn't do. He has to multiply by this factor here to hit the time that he measures, so that he would get the time measured by TB, and then again, voila, the ball has dropped at the same speed. Sorry. Sorry to myself, because I drew this, and some of you would have known what this alpha is, and I will just quickly let you in, even though I dislike doing this, because we haven't spoken about light. It's the speed of light or speed of causality and all this, the height, whatever. It's the time information takes to reach us, and it's better understood here. VTA is the distance, and by speed, it's the time it takes. It's actually better understood this way. TA minus D by C equal to TB. where D is the distance that the other room is sitting at from the origin of the room A, and the D is the distance between the rooms, and then divided by the speed of light. That's how long the information takes to reach you. Okay. Right, and then just one more thing before we go to the historical context here. What happens in the previous, in the Galilean transform that we saw, that xa minus VTA, now we have to, in Galilean it doesn't really matter, they think that the time is the same, was xb. What happens if the room starts coming back? You wouldn't have xa plus Vt, because that would lead to problems. The room is coming back, but then xa is still increasing. You can't have that. So you would have to do something like xa plus Vt minus d equal to xb. And the reason why you do this is because, let us say that this is the origin, and if something is moving away from me from the origin, and it started at the origin at time t equal to 0, then I have the position of this thing x equal to Vt. But when it starts coming back, then it's not x minus Vt, right? Because minus Vt is here. So it have to be minus Vt plus d, and d is the distance, the point where it started coming back. Okay. So when the ombre b starts coming back, then we would just have to modify this a little bit. Firstly, it would be this, because the speed, the velocity has reversed, and minus d. And this you should verify on your own if you're confused about this. But the reason why I bring this up is because for time, you would have Vta by c minus d by c. Sorry, Pb. The reason I bring this up is because when you could again take Ta common here, and you could see that 1 plus V by C. So there is some offset, but time is taking now faster for when ombre A is coming back. Because if you remember, the watches, while they were far away, they appeared to be out of sync. When they were brought back, they were back in sync. So the clock that falls behind, when you move it back, it again catches up, and then it's again at the right time. Yes, so when it comes back, the same ball that you had dropped, which looks like this when dropped in A, which looked like this when dropped while B was moving away in B, would look like this when B is moving towards A. And then it would look like it dropped faster. So you always have to account for time dilation when something is moving away or towards you. Otherwise, you would think that they are moving around slowly or moving around faster, depending on their speed. But really, they are not, because if you're in that frame, you would not think that I am moving suddenly moving faster. This is another thing. If time doubled its speed, we wouldn't know. But the reason why we still call it apparent time dilation, not real time dilation, is because once he comes back, it's just reversed. It's not really like if ombre A and ombre B wouldn't be any younger or anything. Okay, because even if you while going aged slower, no, you would actually. What I thought was, even if you could age faster and slower, you would always forget what I said. Point is that when ombre B comes back, he is at this exact same age as ombre A. Ombre A. So it's apparent time dilation, but it's actually something that you could see happening. And if you have even the most basic telescopes or even binoculars, you could measure it happening. And this is the story now, historical context. There was a big problem called the problem of longitudes in navigation. When people started going from Europe to the New World, which was the Americas, they had to cross the Atlantic Ocean, and it's so big that you would not see any land for a long time. And as you're crossing the Atlantic Ocean, you don't know how much distance you have traveled around the Earth. So you don't know your coordinates, and that's a big problem. Now, you would immediately come up with a solution that why don't you synchronize a watch with London or wherever, Paris, and then you take that watch with you, and then what time it is, and if you know what time it is and you can measure the stars, then you know what time it I mean you know what time it is in London, and then you can look at the stars and you can know what time it is now, and then you can calculate the difference, and you know what time zone you have ventured into, and then you can calculate the position. The problem is back then they had pendulum clocks, and which were also pretty new, invented by Huygens. I think they were not even like Galileo, I think, was using a sundial or something. They didn't have uh, pendulum clocks even. So, and the pendulum clocks would not work on the ships. They would just be too shaky for the pendulum clocks to function. So Galileo suggested, I'm not even kidding you, that you measure the eclipses of Io, because we know when the moon of Jupiter, which is whose name is Io, this is Jupiter, and it has a moon called Io, which is the nearest moon. When it moves into the shadow of Jupiter, we know the timings of these. I mean, we didn't know when in Galileo's time, but we could create a table of these timings, and all you have to do is look out at Jupiter, and maybe for a while, and then you see that the eclipse and transit. Sorry, eclipse, like in going in and going out of this shadow of this moon, and then you would know what time it is in wherever the table was made, and then you could calculate your position. And then people started taking measurements of these things in under the wing of Cassini, a Danish astronomer called Ole Rømer. Ole Rømer uh, measured the timings, and he found out that it is hard to make this chart. In one of the interesting things, the reason why is because let us say that we are going near to the Jupiter. So by this time the we had all accepted the heliocentric theory. So this is the sun. Is this sun? No, that's Venus. Sun is, I think, this, right? Oh man, I forgot. Earth is this, right? Doesn't matter. This is the sun, as you know from being at the center of the solar system. This is the Earth and this is Jupiter. And as we are going towards Jupiter, and as we are going out of away from Jupiter, the time that Io spends in the Jupiter shadow is different. When we are going towards it, can you guess? Can you guess? Can you guess? Would it be when you're going towards it? It's like that room is coming closer to us, so things would appear faster. And when we are going away from it, the room is going away from us, and things would appear slower. So he measured the timings, and he realized that this is a huge, like, it's as if the moon going around Jupiter, it does it faster when we are moving this way, and it does it slower when we are moving this way, and it's a continuous change. It's not like it flips one day. It's a continuous change. When we are here, we should get the like absolute, like, correct position, because we are moving in this direction. And this is enough for history. I was reading Wikipedia, so I could just recite the whole Wikipedia page for you. But now I would like to show you that it is actually slower. And I do this in the software in an app called Stellarium. So here you see Jupiter, and Io, you can't see it, maybe it's behind. It's actually current time. So I actually saw Io. No, here is Io, because it's exactly how Jupiter must look like right now if you could see it. Okay, now we are going to just speed time up a little bit. Now you can see that Io is, well, going around Jupiter. You can also see other moons of Jupiter, but just pay attention to Io. Also notice that it comes out of the shadow here because sun is in this direction. All right. How is my... Did you see that my cursor was gigantic for a second? Okay. Now what we'd do is we'd go forward in the calendar year. Now see, Jupiter is getting smaller, and that means look at the orbital speed of Io. Just notice it. I would not tell you whether it's faster or slower. It's your job, and I'm gonna ask you to eyeball it, or you can even get a stopwatch to do this. Even smaller, And now again it would start getting bigger. See, it's getting bigger. Can you see it? It's actually faster when we are going towards Jupiter. And I mean, ideally, as a teacher, I should get a stopwatch and do this, but I eyeballed it and it looked faster and slower. And yeah, so this is time dilation. It actually, you can see it. So if you have even the most rudimentary of telescopes or a binocular, and then you just, well, it would be a pretty difficult task looking at Jupiter all the time. There are other challenges. Sometimes you can't see Jupiter at night at all. Sometimes it's too close to the sun. Sometimes you have to wake up at wrong hours. Sometimes it's I'm not saying that you would be able to do this. I mean, you could do this, but you would have to do this and nothing. I mean, it would be a pretty dedicated exercise, but go for it if you can. But then it wouldn't look like this simulation. It would look like a bunch of timings written down on a sheet. I think it still would be fulfilling. Fulfilling. Okay, this was it for this second revolution. I would call it Römerisch, Romerian transform, that what we saw here. And now in the next video, we would come to special relativity, the Lorentz transform, the Lorentz-Einstein uh, Poincaré transform. Why this would still not correct. There are more things that ombre A, B, and C's have not accounted for yet, and they are going to show up. And we would also, of course, talk about the physics and the discussion and history of. This is why, I mean, the third video is why I started making this series in the first place, because I read Einstein's book and then I thought, wait, it was easy all along. Then everyone made it so difficult that it took so long for me to understand this, and why not let's begin at the very basics, because relativity is a concept that predates Einstein by a few centuries. So, all right. So, thank you for watching, and I hope to see you again. I mean, you hope to see me again, I know that, in the next video lecture.